all can be illustrated with this simple, like, pool table kind of example. So, I mean, it's a really simple experiment, and we just don't have it anywhere, you know.
No, because nobody's ever played pool, have they? Talking balls again, are we?
So what actually happens? So these are all the same mass. So what actually
Why don't you try it? See what happens.
Happens when I take this 100 momentum ball and I hit both of these at the same time? Because we know if that was a Newton's cradle, what would happen is the energy would just be transferred.
So what you're saying is, like in a Newton's cradle, it would be an elastic collision. What you're talking about there is probably like a 1,000,000 to 1 shot anyway, because you'd have to hit both balls at exactly the same time. So because the chances of actually doing it is very slim. But you're going to talk shit about what would happen.
Right, if this was just one ball hitting one ball, this one would stop, this one would go, and I wouldn't have any increase in anything. But in this example, now I got twice the mass. I'm going to hit them both at the same time, twice the mass. Now, am I going to get, by rational theory, right? I don't have a choice here, right?
Now, it's interesting now because you've drawn angles, so you do understand that they go off at angles. If you were to do this and get it exact, they would go off at a 45-degree angle, both of them.
I mean, what's the rational choice? This has to be 1/2 the velocity, and this has to be 1/2 the velocity, right? There's no choice here.
Right, so you're saying it has to be. Again, you've not tested it, and if they both went off at 45 degrees at half the velocity, you have now not conserved momentum, and you've not conserved kinetic energy, which in a perfectly elastic collision, that's what you would get, conservation of both. So you're arguing here for non-conservation of momentum.
This won't be the same kinetic energy. See, the problem is half this velocity.
Correct, you won't conserve kinetic energy in your example here, like you wouldn't conserve momentum as well.
Velocity, see, I make the velocity half and I make the mass twice. Because of that quadratic, the v squared part, okay, that just means that, no, this now has half the kinetic energy. So somehow I lost,
No, you wouldn't lose any energy. You would conserve it.
This had 100 kinetic energies, all right, this only has 50, both of these combined. So somehow I lost.
But you're making the assumption that they go off at half the velocity, which, again, if they did, kinetic energy wouldn't be conserved, and also momentum wouldn't be conserved, because momentum is a vector. So they're going off at equal and opposite angles. So the ball's coming in one direction, those go off at angles equal opposite, so that cancels. So we're looking at how far those two balls move in the vector in the forward direction. And if they were going half the velocity, like you're claiming here, that would not conserve momentum.
Lost half the kinetic energy. It doesn't make any sense that I lost it. Where could I possibly lose it? It's no different.
You didn't lose it. Again, you're making an assumption.
Different than hitting the one ball. I'm just hitting a ball and making the other one go. So again, this simple experiment sort of just proves the case, doesn't it? I mean, I think we all know that this...
No, it doesn't prove anything. It proves that you're fucking stupid.
These two balls will only go half the velocity.
But they don't. That's what you claim, that's what you say. You haven't tested it, and that's not what happens.
And that's what's actually going to happen. And the fact is, there's going to be half the kinetic energy, because kinetic energy is a fable. It's not real. And what there really is...
The thing is, you think this is some sort of gotcha, like, oh, I've got you. No, again, you're just showing your complete fucking ignorance.
Going to be is the same momentum. I'm going to have the same MV here, the same mass moving as I had mass moving here. I'm going to have this...
No, you're not if they go half the velocity, because they're moving off at angles. So again, if they're going half the velocity, you've not conserved momentum. Because momentum's a vector. Direction matters.
Same amount of motion, okay, quantity of motion, quantity of mass and velocity that I had here. So I'm not going to lose anything. It's all conservational, and it all makes so.
It's not, your example here is not conservational.
For people who have any interest in pool, okay, to explain exactly how that, what would happen here, you know.
So what would happen there is they'll go off at 45-degree angles. Say the incoming ball's going 10 meters per second and it hits those two exactly. You get the perfect shot. They will go off at 45-degree angles at around 7.07 meters per second each in the respective angles. The fact that they're going that velocity conserves kinetic energy. And after a second, so first ball's coming in 10 meters per second, so in 1 second it covers 10 meters. Those two balls are going 7.07 meters per second, so obviously in 1 second that's the distance it will cover, but they're going at angles. So imagine those two balls are going off and forming like a triangle. Draw a straight line from the centre that goes straight up. So you've got 7.07, 7.07. So when you go straight up, you've got around 5, which should be half of the 10. Because that's how far those masses have moved in a direction, in a vector. So momentum's conserved and kinetic energy is conserved because they aren't going half the velocity, as you claim. You just make that shit up.
If you hit both those balls at the same time, what's going to happen? And like I said, I think we all know what's going to happen. They're going to leave with 1/2 the velocity, and there's not going to be any explanation.
But there is an explanation. They don't go half velocity. Again, you just made that shit up. Try it, test it.